Welcome to another Explainer. Today, we're tackling an absolutely fascinating software engineering challenge that perfectly highlights the difference between writing code that just barely works and writing code that is beautifully optimized. It's the sequential digits problem. If you've ever found yourself staring at a seemingly simple math-based coding problem, only to realize that checking every single possibility is going to crash your system or time out your compiler, well, you're exactly in the right place. We're going to see how to completely bypass this massive billion-number trap using a couple of incredibly elegant strategies. Okay, let's dive into this. Before we get to the heavy lifting, we got to establish exactly what a sequential digit is. Simply put, an integer has sequential digits if and only if each digit in the number is exactly one more than the previous digit. Think of those everyday numbers you might absent-mindedly type on a keyboard, right? Like 1, 2, 3, or 2, 3, 4, or even 4, 5, 6, 7. Every step to the right increases the value by exactly 1. The challenge we're given is to return a sorted list of all these sequential numbers that fall within a specific range, defined by a low bound and a high bound. Sounds pretty simple, right? Well, hold on, because here's where our intuition can totally lead us astray. Your very first instinct might be brute force. You're given a low number, say 100, and a high number. Why not just write a loop to go through every single integer between them, check if the digits are sequential, and save the ones that are? Here's the catch. That high boundary constraint can be massive, up to 10 to the power of 9. That is literally a billion. If you linearly check every single number up to a billion, extracting and comparing digits along the way, you are falling straight into a massive performance trap. It's just wildly inefficient. We need a way to completely skip all those invalid numbers. Which brings us to approach 1, the sliding window. Let's see how we build our first solution. This source material highlights a seriously clever workaround that leans entirely on a predefined sequence. Take a look at this master string, 1, 2, 3, 4, 5, 6, 7, 8, 9. Every single sequential number that can possibly exist in our base 10 system, it's just a substring hiding right here. 1, 2, 3 is in there, 5, 6, 7, 8 is in there. So instead of iterating through a billion numbers, we really just need to pull the right slices out of this one single string. To pull this off efficiently, we use boundary filters. Think about it. If our target range is between 100 and 300, we know for sure we're only looking for 3-digit numbers. We don't need to check 2-digit numbers, and we definitely don't need to check 8-digit numbers. In languages like C++, we can just use a built-in function like std.toString on our low and high inputs to instantly determine their digit lengths. These lengths act as perfect filters so we don't waste a single CPU cycle looking at substrings that are way too small or way too large. So how do the mechanics of this sliding window actually operate? It's pretty cool. You set your window size to the minimum length, let's say 3 characters. You start all the way at the left of our master string and slice out 1, 2, 3, then you just slide one step right to 2, 3, 4, then 3, 4, 5, and so on. If it falls between our low and high bounds, we save it. Once you finish that length, you bump up the window size and do it again. And here's the best part. Because we slide left to right and start from the smallest length to the largest, our output is automatically sorted. No need to run an expensive sorting algorithm at the very end. Plus, since the maximum length is just 9 digits, these numbers safely convert back to integers using std's stoy without any risk whatsoever of a 32-bit integer overflow. Now let's explore approach 2, the BFS graph walkthrough. As clever as that string slicing is, let's shift gears to a slightly more standard generalized approach. We need to stop thinking about checking numbers and start thinking about generating them dynamically, using a tree data structure and a breadth-first search, or BFS. Every tree needs a root, right? Or in this case, multiple roots. Our BFS queue kicks off with all valid single-digit prefixes. That's the numbers 1 through 8. Notice we intentionally and specifically omit the number 9. Why? Well, because the core rule of a sequential number is appending a digit that's exactly 1 greater than the last one. If we start with a 9, the next digit would have to be 10, which obviously isn't a single digit. It would generate 910, breaking our sequential rule instantly. So our seed values are strictly 1 through 8. Let's trace how this queue actually flows. BFS operates on a first-in, first-out, or FIFO basis. We pop the first number off the queue, which is a 1. We look at its last digit, add 1 to it, and push the new combined number, 12, right back into the queue. Then we pop 2, generate 23, and push it back. Because it's a FIFO queue, we completely process all those single-digit seeds before we ever touch the 2-digit numbers. This naturally expands level by level, from length 2 up to length 3, and so on. And exactly like the sliding window, this absolutely guarantees the numbers are generated in a strictly increasing, perfectly sorted order. The actual C++ math behind this is beautifully simple cyclic math. When you pop a number, you need its last digit. You find this by using the modulo operator, num%10. So if the number is 12, 12% 10 isolates the 2. The next digit we need is simply last underscore digit plus 1, which is 3. To append this mathematically, without cheating and using strings, you take your original number 12, multiply it by 10 to shift it left, making it 120, and just add the new digit 3. Bam, 123. We push 123 into the queue and just keep rolling until our generated numbers finally exceed our upper boundary.
And this brilliantly illustrates our final section, complexity and wrap-up.
Understanding different data structures is powerful, but how do they actually stack up against each other? Well, when we compare the sliding window against the BFS graph traversal, we see something incredibly special. Despite the problem allowing constraints all the way up to 1 billion, both methods share a time and space complexity of big O of 1. Constant time. That means execution time and memory usage stay completely flat, no matter how massive the input gets. But the real reason both are constant time? It all comes down to a hard mathematical limit. Check this out. Out of 1 billion possible integers in our constraint range, there is a strictly bounded state pool of only 36 total sequential numbers that can ever even exist. That is literally it. From single digits all the way up to the massive 9-digit 1, 2, 3, 4, 5, 6, 7, 8, 9, there are only 36 possibilities in the entire base 10 universe. Our algorithms, whether they're sliding a window or popping a queue, will never do more than a few dozen operations. By focusing on generating the right answers instead of checking 1 million wrong ones, we bypass that billion number trap entirely. So the next time you're facing a problem with massive numerical constraints, I want you to take a step back, ask yourself, am I iterating through 1 million wrong answers just to find one right one? Whether you use a clever sliding window over a master string or a perfectly ordered BFS queue, you now have the exact tools to generate solutions in constant time. Are you ready to ditch the brute force trap and apply these elegant big O of 1 optimizations in your next technical interview? Thanks for joining me on this explainer. Keep optimizing and ask yourself, what other massive computing problems are out there, just hiding a tiny bounded state pool right beneath the surface?